Hi everyone, my name is Cheng Yuxuan. I currently is an MPhil student at Beijing Normal Hong Kong Baptist University, China. I currently focus on scale imbalance problem in computer vision. And the paper I present today is rethinking dynamic scale training with regularization effect and data pool. So let's figure out what is the scale imbalance problem. There's an image from the VOC dataset. The blue box is the ground truth, and the red box is the prediction box from the detector. We can observe that the larger object clearly have more detailed feature and occupy the larger size in image. The smaller object not only have less feature, the remaining feature also have a lot of noisy, very hard to separate from the background. And therefore, large object can produce more loss value than small object. Such loss value can make the parameter of large object pressure the parameter of small object, like squeezing them out. The detector will favor large object more, unlike the class imbalance problem, which can be solved simply by adding more images. The scale imbalance problem is a natural phenomenon. Therefore, we need to do something to address this problem. So let's figure out what is dynamic scale training. The dynamic scale training for object detection is from paper published on the CVPR 2020. This paper introduced a new data augmentation paradigm, the feedback-driven data augmentation triggered by loss value ratio. So in one iteration, that's mean in one bench, a small object loss value ratio is less than a threshold. The threshold is 0.1. Then the data augmentation will be triggered. Four images will be resized into quarter size, then stitched together. In this way, the average size of object will be reduced. However, we can observe that there are still large objects inside the stitched images. There are no guarantee that this data augmentation will produce the enough small object, and the background is different from normal images. So like these images, we can clearly see that directly resize the image into smaller image. The relationship between the object and the background is unchanged. This relationship is different from the actual small object images. However, we understand from a lot of paper the background, especially the background around the object, is vital for detector to recognize the object. And there are paper present the experiment using data augmentation in training, then fine-tune the detector with the original image at the final stage of training, so they can improve the performance. Therefore, this is our first motivation. We maybe need to maintain the original object background relationship. Therefore, we propose data pool, a new framework for colleague fashion data augmentation. The framework contains three steps: analyze, search, and synthesize. The analyze strategy will divide all image into patches, but try to preserve the background as much as possible. The search strategy is try to search the potential patch with the custom rules. We can make the rules by ourselves, like custom the object range from 0 to 32 times 32, and that's the small object range. Or we can make a larger, like from 0 to 64 times 64, and like 0 to times 0 to 96 times 96, that's the large object range. Then finally, we can synthesize the colleague image with the searched patch with limited cutting and resizing to preserve the most possible background. The advantage of such a framework is it has a larger degree of freedom while preserving the most possible background. The analyze strategy is like this figure. Because we can custom the object range as we want. The analyze strategy will search for the suitable patch inside the image, like this area, like this blue box area. First, the analyze strategy will start randomly from one object, then expand to another object. And so we continue to repeat this process until we find the object which is not belong to our custom range. And so we have an area, one patch area. Then we try to expand this area with the background as much as possible. There are many different expand possibilities, so we can produce different patch with one area. And finally, the data pool image is shown like the upper figure. We can see that the figure not only have a small object, but a lot of background, with only a little bit of waste of image area, whereas the mosaic image waste a lot of area. That's what we try to avoid. The second motivation is the same data augmentation strength through the training process. We can observe that the trigger mechanism in the dynamic scale training is static, which means the data augmentation bench probability is the same through the training process, like the blue line. This is not aligned with intuition because because we understand that with the learning rate becomes smaller, the inference ability of a large object and a small object will get closer. So the, the, the way to align with the intuition is to make the data combination strength or possibility gradually reduced during training. And we can also to reduce the determination strength, but we choose to reduce the probability, the trigger probability, by directly using the cosine annealing learning rate schedule, like the red line. So we simply put the cosine aligning learning rate function inside the original schedule to form a hybrid schedule, like this algorithm. The hybrid scheduler have two controller. The outside is the original loss value ratio based controller, like the line 2. And the inside controller is the cosine annealing learning rate function, like the line 7. The output of cosine annealing learning rate function is controlled by the epoch number. At the beginning of training, the output is nearly 1. And at the end of the training, the output is nearly 0. So even the small object loss ratio is less than 0.1. We still have to pass the cosine annealing learning rate controller. And here's the experiment result. The table 1 is for data pool. We can observe that the object range is 0 to 64 times 64, and the batch size is 32. We have the best performance. As for the hybrid controller, we can achieve the nearly 1 point at all size of COCO dataset. We divide the COCO dataset into one dataset, full dataset, and half dataset, and a quarter dataset. And we can see that the hybrid controller nearly improved 1 point across all different size of dataset. That's all. Thank you for listening.